carbon anode plant expert, and he is working for many years in this area. He joined Bharat Aluminium Company Limited in 1974. So, but basically, he's 3 years senior to me. I joined Balco in 1977. So he's one of the authority. He is one of the authority in anode in carbon area, and he worked in Emal, he worked in Alba, he worked in some other Dubal, and also in Nalco. So he has a working in the carbon plants and coke calciners. So he is the authority, and I really appreciate and his knowledge and his long working years in the carbon plant. And now still he's continuing to give his consultancy services to many companies in Middle East and Indian aluminum smelter carbon plants. So I welcome Mr. Khalil Khaji. And I will request Priyanka of IBAAS office to start the presentation. Welcome to you all. So there are already 26 to 30 delegates and 30 participants. So we may get some more participants in coming minutes. So you are all welcome, and I request Priyanka to run the pre-recorded presentation. And then it will be a live question-answer session.
Respected Dr. Ashok Nandi and dear friends, welcome to my presentation on optimization of carbon anode quality. Aluminium is produced by electrolysis of alumina in Hall-Héroult cells. In Hall-Héroult cells, carbon blocks are used as anodes. The carbon anodes conduct electricity into cells and provide carbon for the reaction with oxygen released during electrolysis of alumina. About 400 to 440 kilograms of carbon anodes are used for 1 ton of aluminium production. Pre-baked carbon anodes are produced in captive carbon plants using advanced technologies for green anode production, anode baking, and sealing baked anodes with stem brackets. Carbon anodes of optimum quality are needed for the smooth operation of electrolysis cells. The carbon anodes supplied to reduction cells are expected to have good apparent density, high resistance to thermal shock, low electrical resistivity, minimum chemical reactivity, zero physical defects. Carbon anodes are consumed continuously during aluminium production. Baked anode density strongly influences anode life in the cells and affects properties such as mechanical strength, permeability, and electrical resistivity. Therefore, anode density must be optimized without adversely affecting other key anode properties. The main raw materials used in the production of carbon anodes are calcined petroleum coke as dry aggregate and coal tar pitch as binder. The figure shows the baked anode density improves with increase in vibrated bulk density of cokes. Calcined petroleum cokes are obtained by calcining green petroleum cokes in rotary kilns or in vertical shaft kilns. The rotary kiln calcined cokes generally have low VBD, while shaft calcined cokes have high VBD. It is a general practice nowadays to blend low VBD cokes with high VBD cokes to have an higher average VBD coke mix. In this way, we can achieve higher baked anode density. Coke is a granular material containing both large and small particles. During silo storage, these particles segregate. Larger particles move toward the silo periphery, while smaller particles remain near the center. When the silo level is high, the extracted coke contains more fine particles. As the level falls, more coarse particles move into the center and are discharged. This changes the particle size distribution of coke sent to the paste plant, which in turn alters the dry aggregate granulometry and causes undesirable variation in anode density. To overcome the problem of variation in granulometry of extracted coke, planetary screw conveyors are installed at the bottom of the silo. The planetary extractor moves particles from the periphery of the silo towards the silo center. The extractor also rotates around silo bottom. It enables a stable, consistent granulometry of coke taken out of silo. The adverse impact of particle segregation is eliminated. Cokes available in the market have more fines and small size particles. The fines and small particles are separated from large grains by improved methods of screening. The fines and small size particles are used to produce fines fractions. The large particles are used to produce coarse fractions. The large grains are subjected to minimum crushing using Rodax crushers, roll crushers, and cone crushers. The large grains have higher VBD and provide strength to the anodes. The white spaces between large grains are filled with fines fraction, thereby achieving higher VBD dry aggregates. This helps to have higher anode density. Analysis of data of many carbon plants over a period of many years has shown that the baked anode density improves with increase in dry density of green anodes. Dry density is mass of particles in unit volume without coal tar pitch. It is highest mass of dry material filled in unit volume. By adjusting the granulometry of large and small size particles and by filling the wide spaces with optimum amount of pitch, high dry densities are obtained. There is impact of percentage of large particles in dry aggregate on the dry density of anodes. The particles above 13 millimeter should be about 8 to 10% maximum to have high dry density. Higher content of large grains drops the baked anode density. There is also impact of percentage of ultrafine particles in dry aggregate on the dry density of anodes. The particles below 0.03 mm should be about 13.5 to 14.5% maximum to have high dry density. The dry aggregate is heated before mixed with liquid coal tar pitch binder. The heated dry aggregate allows the liquid pitch to remain at high temperatures, lowering its viscosity so it can flow more easily into the voids between grains and coat and fill the micropores of the particles. As a result, the mixer produces a denser green paste. Mixing power helps to achieve higher anode densities. Baked anode density improved from 1.565 to 1.590 grams per cubic centimeter, as the mixing energy increased from 5.5 to 7.5 kilowatt hours per ton of paste for the same blend of cokes and dry aggregate recipe. Mixing energy enables filling of micropores of coke particles with binder. Higher the mixing energy, higher is the effectiveness of filling micropores with binder as well as coating of coke particles. Use of paste cooler enables mixing of dry aggregate with coal tar pitch binder at higher temperatures. It is used to homogenize the paste as well as to cool the paste for compaction in the vibro compactors. Vacuum assisted compaction allows the paste to be compacted at higher temperatures. It rapidly removes volatile fumes from the coal tar pitch, preventing them from becoming trapped in the anode mass and causing cracks. The green paste is more plastic at higher temperatures. It can be compacted more effectively, resulting in higher anode density. When cold anodes are placed in the hot bath of electrolysis cells, they experience thermal shock. Due to uneven expansion in different directions, cracks are initiated in anodes. The cracks propagate through the anode mass, often causing breakage at the anode corner. The broken carbon pieces fall into the bath, create short circuits between the anode and cathode, form spikes, reduce metal production, and generate dust in the pots. To avoid disturbances to pot operation, the anodes must have adequate resistance to thermal shock. This is an example of anode thermal shock cracking. The graph shows how thermal shock cracking in anodes was addressed in a plant. As the cell line current increased from 350 kA to 385 kA, anode breakage due to thermal shock rose from 0.5 to 2%. The anode problem was measured as the percentage of extra anodes supplied beyond the scheduled requirement for the reduction rooms. To address the problem, the dry aggregate calorimetry was modified to increase the grain to sand ratio from 2 to 4. Anodes produced with the revised granulometry were then supplied to the pot rooms. The figure shows the resulting reduction in anode problems. Dry aggregate composition strongly affects the anode performance in cells. At the start of plant operation, the anode grain to sand ratio was about 2. Increasing the dry aggregate GSR to 4 reduced anode problems, showing that higher GSR reduces anode thermal shock cracking. The anode thermal shock resistance can also be increased by providing slots in the anodes. Slots prevent crack propagation. The number of slots made in the anodes depends on the size of anodes. The slots could be cut into baked anodes or formed during compaction of green paste. In addition to improving anode thermal shock resistance, the slots also reduce bubble resistance under the anodes. Anodes need to have low electrical resistivity to minimize anode voltage drop. Higher resistivity increases cell voltage drop, which raises power consumption and metal production cost. It also contributes to greater greenhouse gas emissions because more electricity is required. The baked anode electrical resistivity increases with increasing sulfur content. Anodes having higher sulfur content show higher electrical resistivity. Electrical resistivity is influenced by the number of electrons that flow through the anode mass. Each carbon atom has two electrons in its outer orbit, and these electrons are released easily from the outer orbit to achieve orbital stability. The electrons released from the outer orbits of carbon atoms form a cloud of free electrons. These free electrons ensure the flow of electricity through the anode mass. As opposed to this, each sulfur atom has 6 electrons in the outer orbit and needs 2 electrons to fill its outer orbit to achieve orbital stability. The required electrons are made available from the cloud of free electrons. The higher the number of sulfur atoms in carbon anode mass, the higher the number of free electrons captured by sulfur atoms, reducing the number of free electrons available for conducting electricity. It may therefore be said that the anode electrical resistivity increases with increase in sulfur content. Sulfur content in anodes is influenced by the sulfur content in calcined petroleum cokes, the quantity of pitch added to the anodes, and the level of anode baking. The sulfur content in the calcined petroleum cokes available in market is in the range of 2.5 to 3.5%. However, a few calcined petroleum cokes have a sulfur content of 1 to 2%. Low sulfur cokes are limited due to depletion of sweet crudes. Anodes are produced using blends of high sulfur cokes and low sulfur cokes. The average sulfur content of cokes and anode is reduced. Coal tar pitch has relatively low sulfur content in the range of 0.5 to 0.8%. It is converted to pitch coke during anode baking. The pitch coke is pure, has low sulfur content and elemental impurities. With the increase in pitch addition, the quantity of coke with low sulfur content increases in anodes. There is an overall reduction in the sulfur content of anodes. Increased pitch addition increases contact between coke grains. Reduction in sulfur content and increase in contact at the particle interfaces explain the reducing trend in anode electrical resistivity. The graph shows the changes in anode electrical resistivity with the quantity of pitch added to the anode. Some of the sulfur atoms leave the anode mass during anode baking, and this leads to the desulfurization of anodes. The higher the temperature of anode baking, the higher the desulfurization of anodes. The anode desulfurization depends on the peak flue gas temperature and the soaking time during anode baking. The desulfurization is high in anodes made of high sulfur cokes. Higher the baking temperature and higher the soaking time, higher is the loss of sulfur from anodes. Electrical resistivity of carbon anodes decreases with increasing lattice constant. The lattice constant increases with increasing peak flue gas temperature of anode baking. Electrical resistivity also decreases with increasing baked anode density. Dense anodes provide continuous passages for the smooth flow of free electrons. Anode chemical reactivity affects carbon consumption during aluminum production. The theoretical carbon consumption is 334 kilograms of carbon per ton of aluminum. but actual industrial consumption is typically 400 to 440 kilograms of carbon per ton of aluminium. The excess consumption results from secondary reactions between carbon and carbon dioxide, air burning, and erosion of particles from the anode bottom. Lower anode reactivity suppresses these secondary reactions and reduces carbon consumption. Reactivity residue is a measure of anode chemical reactivity. Higher the residue, lower is the chemical reactivity. The net carbon consumption decreases with increasing carbon dioxide and air reactivity residues. Impurities in coke have adverse impact on CO2 reactivity of anodes. It is known that elemental impurities such as sodium, calcium, and iron act as catalysts for the reaction between carbon dioxide and carbon at the bottom of anodes. The figure shows there is a sharp drop in CO2 reactivity residue when the impurity content exceeds 0.065%. Sodium has highest influence and acts as a catalyst for the Baudard reaction at 960 degrees centigrade. The sodium is contributed mainly by the recycled butts. Bath cleaning of butts in rodding shops has a big impact on anode reactivity. The CO2 reactivity residue improves with increasing pitch content in anodes. The CO2 reactivity dust and air reactivity dust reduce with increasing pitch content. This is due to better bonding between the particles of dry aggregate. Air reactivity residue decreases with increasing vanadium content in anodes. The cokes from sour crudes have high vanadium content. Blending of cokes from sweet and sour crudes helps to bring down the vanadium content of anodes. Desulfurization of anodes creates permeability and additional surface area for secondary reactions. Excessive desulfurization is undesirable as it can increase carbon consumption. The table summarizes impact of pitch addition, metallic impurities, and desulfurization on CO2 and air reactivities. The impacts on net carbon consumption are also indicated. Anodes supplied to reduction rooms must be free from physical defects. The anodes must be free from segregation of particles on anode surface, horizontal and vertical cracks, cracks around the stub holes, bulging, peeling of surfaces, peeling at anode chamfer edges, air burn, deformation of stub hole fluids and bottom. Segregation in anodes is eliminated by adjusting grain size, dry aggregate granulometry, and improved paste mixing. Horizontal and vertical cracks are eliminated by avoiding excessive paste compaction and by ensuring vertical movements of mold and top tool. Cracks around stub holes are eliminated by adjusting forming temperature, fines and pitch addition to the paste. Bulging of anodes is prevented by adding optimum amount of pitch based on dry density method. Peeling of anode surfaces at anode corners, air burn, and deformation of stub holes are prevented by following proper practices of packing and unpacking of anodes, filling of packing coke, and adjustment of air blower parameters. This is an example of anode segregation and deformation of anodes. This is an example of shoulder cracks and packing coke sticking in the stub holes. This is example of horizontal and vertical cracks, also between the stub holes. Cracks around the stub holes can be seen in this slide. There should be no loose particles on the anode surfaces. There should be no peeling of the anode surfaces and also no peeling of the anode chamfer edges. This is an example of broken corners. I would like to summarize my presentation. Baked anode density can be optimized by blending low and high VBD cokes, by minimizing variation in the granulometry of cokes extracted from silos, using selective screening and crushing, adjusting dry aggregate granulometry, mixing the dry aggregate with binder at high temperatures, applying optimum mixing energy, and by using vacuum-assisted paste compaction. The anode thermal shock resistance can be improved by increasing the grain to sand ratio of dry aggregate and by providing slots in anodes. The electrical resistivity of anodes can be reduced by reducing sulfur content in anodes, by increasing the LC, and by increasing the anode density. The sulfur content can be reduced by blending cokes through pitch addition and by baking at higher temperatures. The chemical reactivity of anodes can be minimized by reducing metallic impurities, by reducing excessive desulfurization, by adequate addition of pitch, and by equalizing the reactivities of pitch coke and calcined petroleum coke. Thank you for listening. The presentation is open for discussion.
Hello.
Hello, sir. Can we ask questions now?
Yeah. Please. It's Mr.
Okay.
Khalil Khaji ji, please come online. Please start your questions.
Yes, sir.
Yes,
Mr. Khalil
I'm
ji.
Das speaking.
Hello.
I'm Das speaking. Sir,
Yes,
you hear me?
yes. I'm able to hear you, Satyanarayan.
Sir, it was an excellent presentation with a overview of optimization of anode quality. I have a small recapitulation of my working in Spotline and all that. Yeah, we used to come across during one period half fallen anodes. Anodes were falling after placement, after 2-3 days, just
Yes.
from the middle of the anode or 3/4 of the anodes, it was falling. And we were clueless. Somebody said it is due to bad quality of pitch or some raw material problem. Is it a thermal shock or?
Yes, this problem is called anode slabbing. And anode slabbing can be reduced by increasing the grain to sand ratio or by modifying the granulometry of the dry aggregate. And there is one more reason why the anode slabbing occurs. If there is a frequent start and stop of the paste plant, that leads to this problem. It is like this. In the vibro compactor, you will be putting cold paste, and over that you are going to put fresh hot paste. The binding between the hot paste and the cold paste in the vibro compactor is not that good. And these things lead to anode slabbing. That is why it is important not only the adjustment of the dry aggregate granulometry, but to keep the paste plant running continuously. Frequent start stops have impact on the anode performance in this manner, in the manner of this anode slabbing. These anode slabbings are more dangerous than corner cracking.
Yes, sir. You are right, sir.
Yeah.
Frequent stoppage was a problem in those days, and
Yes.
that was leading to non-uniform height, non-uniform, non-consistent density, and all that.
Yes, true. Yes.
Thank you.
Yes, Mr. Vivek Saxena, any question?
No, somebody else was asking. I think. Anyway, sir. First of all, sir, it was a very nice presentation, and the same way as enthusiastic you are, so same way you are there in this also. For this high sulfur cokes, probably we are the only two people who believe that sulfur has got a direct bearing on the electrical resistivity.
Yes.
Sulfur, apart from say sulfur, can we do something so that that impact of sulfur, the positive impact of sulfur for CRR can be there at the same time, the negative impact on the ER can be mitigated?
Yes. Sulfur acts as an inhibitor for the Baudard reaction. Some amount of sulfur is desirable in the anodes, some amount. More than 2% sulfur in the baked anodes really will not contribute further for reducing the CO2 and carbon reaction. If sulfur is there, let us say between 1.5 to 2% in the baked anode, that is good enough to take care of the Baudard reaction, to inhibit the Baudard reaction. And this is also good for the electrical resistivity, because electrical resistivity starts increasing when the sulfur content in the baked anode goes higher than 2%. If you can maintain by combined efforts of pitch addition, higher level of baking, and blending of cokes, let us say between 1.5 to 2% in baked anode, that is very, very good for the electrical resistivity. It is a both way it is good for electrical resistivity and also CO2 reactivity resistivity. Yeah.
Sir, should we go down on the peak flue wall temperature?
No. If you go down in the peak flue temperature, the loss of sulfur from the anodes during anode baking is less. That is what you do not want. We want to lose sulfur from the anodes, and this loss is dependent on the peak flue gas temperature. Higher the peak fuel gas temperature, higher is the loss. And also higher the soaking time, higher is the loss also. Yeah, both are important.
Now, the way I was thinking, like if you have got the high sulfur coke, and if the temperature is high, then desulfurization will be more. On
True.
those lines, yes. So
I agree with you. It is a trade-off. It is a trade-off. If you bake the anodes at high temperature, it is very good for the pots, though there is a higher carbon consumption. I agree. But carbon dusting is substantially reduced or eliminated if you bake the anodes at a higher temperature, because you are going to make the pitch coke reactivity and calcined coke reactivity is almost the same.
yes.
So you have to have a trade-off. So I would always suggest to bake the anodes at higher temperature, though there is some increased carbon consumption due to the permeability. I agree with that. But you have more gain in electrical resistivity, you save a lot of money. You have gain in the carbon dusting in the pot, which improves your current efficiency. You have more benefits. These benefits offset the losses due to some amount of increase in net carbon consumption.
Yes. Thank you, sir.
Thanks. There is a question from Mr. Chinmay Pathak. Please go ahead.
Yes, sir. Khalil sir, thank you very much for the insightful presentation. I wanted to ask you, so if we increase the bulk density of the anode, so does it impact your anode production? And if it does, then what is the percentage? Is there any thumb rule?
If you increase the bulk density of the dry aggregate, anode density increases. If anode
Yes.
density increases, its life in the cells
Yes.
can be longer. In fact,
Okay.
the number of anodes you need to supply
Yes.
comes down. In fact, it helps the paste plant, not paste plant, it helps the carbon plant as a whole, because the load on the carbon plant comes down, but it helps the pot room people also. I will tell you, it helps in many ways. Pot room
Okay.
people also will have to do less work in changing of the anodes. Frequency of changing the anodes
Changing.
is reduced. So the workload
Okay.
in the pot room also comes down. And there is one more gain. Frequent anode changing disturbs the thermal balance of the cells. So since you reduce the frequency of anode changing, you are
Yeah.
helping the cells to be at a thermal stability and perform better. In fact, there are many benefits of increasing the bulk density of the dry aggregate, which leads to higher anode density. There are a lot of benefits. Not only that, if you want to keep the anode life same, you have the possibility of increasing the current in the pots. So actually there are multiple benefits of increasing the anode density. Yeah.
So actually, last discussion we had IBAAS in Bhubaneswar. So I had met many people from the anode plant as well. So some people were saying, they have less current density in their plant, and some plants have, higher current density. So my
Yes.
question was whether, let's say your bulk density for your baked anode is 1.3 or 1.9, whatever that range is. So is it constant amongst the plant, or does it vary plant to plant, and then that's why the current density is different for different plants?
These are two separate things. Current density is one thing.
Yeah.
Anode density is another thing.
Density is one thing. Yes.
Current density is amperes per centimeter square of the anode.
Yes.
That is how much kiloamp is flowing and what is the cross section of the anode. These decide
Yes.
the current density. While
Okay.
as anode bulk density is decided by the dry aggregate, amount of pitch
Yes.
you add, and the other
Yes.
process parameters. You see, aluminum production is mass based. So
Mass-based,
higher
yes.
the mass in the anode block, longer it can stay there.
Stay there. Okay.
So, well, current density, well, there are a lot of what do you call
Interconnections. They're all
interconnections.
interconnected.
Yeah. You
Okay.
need to spend more time with people like Vivek Saxena,
Yes.
Satyanara, and Das to know
Absolutely, sir.
more. Yeah.
Okay, sir. Thank you so much.
Yeah. Mr. Ravi Nanath. Mr. Ravi Nanath,
Yes,
your
yes.
question.
Khaji Sahab, namaskar.
Good afternoon, Ravinarath ji. So nice to see you. Nice to see you.
Yeah. And I'm very happy to be part of this session. You well explained technically, clearly understood. Only one point, Khaji Sahab, just I want to highlight that this you mentioned that whenever the pitch is increasing, electrical resistivity will be more. Actually, this we have seen.
Electrical resistivity will be less, not more.
Sorry, electrical resistivity will be better.
Yes.
So we have seen this practically, but people also used to ask why electrical resistivity improved. We say answer is that whenever pitch is more, electrical resistivity will be better. But the theoretical concept now we got from you. This is very.
Thank you. Thank you.
Then one doubt, Khaji Sahab, this you mentioned that whenever pitch is more, this air reactivity dust will reduce it. This is also
Yes.
mentioned.
Yes.
So normally we seen pitches increasing with the rotary coke kiln because that is having low VBD.
Yes.
This rotary coke kiln have another advantage is what is that impurities are less.
True.
So this ARD is contributed more because of this low impurity or the higher pitch.
ARD is well, you see, just to you know very well. I did not explain you a lot. Actually, air reactivity residue plus air reactivity dust plus air reactivity loss. All these three together make 100%. All three together make 100%. Now, if air reactivity residue is less, means air reactivity loss is more or air reactivity dust is more.
Yes.
Yeah, they are all interrelated. Now, air reactivity residue is less because of the catalyst like vanadium. So the impact of the vanadium could be much more than the profit you are gaining by adding more amount of pitch. See, there is it is not only the impact of vanadium or impact of the pitch only. There are many factors interplaying. So pitch is good, but if you add more pitch, it creates permeability, which helps the secondary reactions. But the dust need not be more. If you bake the anodes well, dust will not be there. But reactivity residue will be less because of the loss, air reactivity loss because of the vanadium. So dust is actually helped by addition of more amount of pitch and higher level of baking. These two things keep the dust less. Yeah.
Okay.
I don't know. I hope I explained you. Maybe we have to discuss more.
Yeah.
Okay.
Thank you, Khaji Sahab.
Yeah.
Okay. So, Maheshwar Behraji, please.
Yeah. Khaji Sahab, this was the best presentation, very simple and effective and in-depth of the subject. It was real good. Sometimes we face problem in practical operation like people lose coke in magnetic separator, in iron fraction. In mag fraction, they lose coke particles. So is there any method to recover this coke and reuse, or it is not advisable to add with input material because it will increase the iron. So, what is your experience?
Yeah, here we have to use the principle of trade-off. How much coke you are losing? Is it too much coke you are losing, or it is less quantity of coke you are losing? It is
Okay.
better to not to add this coke back into the system. Better. But
Okay.
it depends how much coke you are losing and what is the reason for losing that much coke. Normally, magnetic separators are meant to separate only the ferrous materials. But if the coke is going too much with the ferrous material, there may be other reason why it is happening.
Yeah.
So we have to address that problem. You can help us, actually.
Okay. Thank you.
There are,
Thank you.
sir.
Thank you.
Sir, can I add? Can I add?
Yes,
Actually,
Yes,
the
yes,
drum
Vivek.
magnet when you are operating, so that angle at which it is scraping out, that needs to be checked from time to time. Sometimes it happens that metal goes away along with it.
yes.
But in order to use that, if the quantity of coke is more, then you can use finger magnets or suspended type magnet, and you can eliminate that iron, and then you reuse the coke which is coming, because that will
Yes.
be very fine.
Yeah. Yeah.
Excellent.
Yeah.
Excellent. Excellent.
Good
So,
afternoon, Mallikarjun Rao. Good afternoon.
Good
yes.
afternoon, sir.
Yeah, Mr. Nanda.
Nandaji,
Sugandha,
good afternoon. Good afternoon, Nandaji. Long time seeing you.
Good afternoon, sir. And
Good
as usual, this was an excellent presentation from all angles.
Oh, thank you. Thank you.
I have a small question to ask. What would be the ideal kind of ratio between really needle coke and short coke? And what are the effects on reactivity of really needle coke and short coke in the proportion?
It is quite a difficult question to answer. Actually, this has to be found plant to plant basis. You know, if you like to use short coke, maybe one should start adding a small percentage to the regular, amorphous cokes. Let us say you can start 10%, then see how the anodes are behaving in the pot. After all, pots are the, we are customers actually. Pots are the customers, and we have to satisfy the needs of the pots. So one has to figure out the behavior of the anodes in that plant, because the parameters in the carbon plant, also the parameters in the pot rooms are very specific to the plants. So if you get good results with, let us say, 10% short coke, maybe you can increase it slightly to 15, maybe 20. That way is much better than well, only you can discuss with other plants their experiences, but you need to go very slow, because when you add short cokes, you have to be very careful in carbon plants. I will tell you where is the main problem. Anode baking furnace. The short cokes don't require much pitch, and it is difficult to decide the amount of pitch you add to the green paste. And there can be severe anode sticking problem in the anode baking furnace. It can be a safety hazard. It can be a production loss. In the pot rooms, the problem can be due to thermal shock cracking, because short cokes have got a higher CT, coefficient of thermal expansion. So one needs to go slowly, specific to each plant. So there is no general answer I can tell you.
Okay, sir.
I apologize. I don't have experience also in use of.
Thank you so much, sir. This is actually enough as far as I'm concerned. Okay, sir. Thank you again, and
Sir, you
my
said
really
10%.
regards to you as always.
Oh, thank you.
Yeah, Mr. Anish Pentakota.
Good afternoon, Khaji sir. Good afternoon.
Good afternoon.
Because my name is not Anish, but my son name is Anish. I registered through, means I connected with my son on phone. So that's why it is Anish. My name is Rao, Mallikarjun Rao.
Yeah, I wanted to ask you when you changed your name. Now you explain me.
I am Murthy sir. How are you, sir?
I'm good. I'm good. Thank you. Thank you.
Good, Rao. Very good.
Thank you.
Good to see today all EGA colleagues.
Yeah. Yes, sir. Khaji sir, just the presentation was I like very much because the content which is bring to the more technical. Normally, people used to talk about yes, it is happening, it is happened. But no, it is not like that. Theoretically, what is happening? It is shown the regarding the sulfur related to the electrical resistivity, and yes, I like very much.
Yeah.
Khaji sir, just I have one doubt. Normally, we are doing the blending in a calcined coke. Okay.
Yeah.
At a anode plant, normally we are blending the coke. So two different sources of cokes are there. So these are not the liquid materials. We know everybody because they all are everybody aware. So
Yes.
this is a solid material.
Yes.
The mixing of two solid materials. How we are trying, we are doing that. We are telling that we are doing homogeneous mixing. We are doing it.
Yeah.
But still, it is not a so since it is not a liquid material, it is a some parcel like a select. It is not some selective zones will be there like different so one coke zones different this one. How
Yeah.
it impacts on the selective burning or maybe selective reaction and this one. And one more, the second question. Is it preferentially it is required? We have to do the blending at a anode means carbon plant area, or it is a before calcination is preferential. It is which is the best option to do the the anode performance for point of view. The best option okay, calcined coke is or green coke blending. Which one is the okay? Even though some calciums are doing the blending of the green coke. But if you want to do the specific this one, which is the preferential, and then how much impact of this mixing of two different cokes at a anode plant, smelter area like.
My preference is blending of the green cokes and then calcine. That would be that would give you relatively more homogeneous coke mix. Relatively, that would blending at the smelter site, or you can say the coke entering the paste plant because it is solid material, and actually you are putting them together. You are not actually blending in these plants. The real blending is happening only in the preheating screw where your fractions are going there. But actual blending is not taking place at the entry of the paste plant because they are put on a belt conveyor or a screw conveyor. So there is not real good blending. It is only a mixing that does cause variation in the electrical resistivity and other properties anode to anode. The pots need anodes of reasonably uniform quality or consistent quality. So we have to accept the shortcomings if we are blending at the smelter site. If possible, we should get green cokes blended at the calciner by discussing with them. That coke would be that coke mix would be ideal, but it is not that easy because not easy. Yeah.
Thanks. Thanks. Thanks, Mr. Khalil Khaji. This excellent presentation, excellent discussions, and we all will welcome you all in the IBAAS conference in Jharsuguda, which is going to held in September 9 to 11. So I will particularly request Mr. Vivek Saxena and the team of Vedanta. We have got about 20 abstracts from Vedanta, including from Balco. And we invite all of you to participate, and we'll request Khalil Khaji ji to also come in this conference. Okay. Okay, so actually next presentation will be devoted to this conference only. We will give you all the updates, how many papers we have received, what are the developments, and we will give you all the details. Thank you very much. Thank you.
Okay, bye-bye.
Thank you, everyone.
sir. Thank you, everyone.
Thank
Thank
you.
you,
Thanks,
sir.
everyone.
Thank you, Khaji sir. Thank you, everyone.
Thank you.
Oh, bye bye. Bye.
Murthy bhai, thank you.
Thank you.
Thank
Ravi
you.
bhai, how are
Yes,
you?
yes.
How are you? Where are you?
Here.